Okay, so a couple of dynamics cards move with very little acceleration on the surface. Okay. And we know that we have a little more downhill here than here, so this is perfectly flat. So these aren't exactly Newtonian objects. Newtonian objects move only under the influence of the forces they exert on each other. Okay. Now what I'm going to do, if I keep my arms out of the way, a little spring here, I can press it. And if I release it, well, it's hard to release this thing simultaneously. Okay, and move apart. Which one moved faster? Probably the one I released first, because I didn't get them released exactly. It's almost impossible to get these released. We'll see they move apart. Now the same thing happens if I do this. Okay. Looking at the different perspective. See, this thing pretty much stops. Now it rolls backwards just because it was slow. The backward motion is pretty much just what you get on the slope of the tape. Now, if this thing's moving, you notice this time this thing is moving, right? So we do have dynamic straps. This is more fun. This movements of uncertainty and so forth on the surface. Okay, well, anyhow. What's going to happen if I pretty much double the mass? I haven't checked these. They might be a kilogram. They might be a little less or a little more, somewhere in that neighborhood. What happens if I release these together? What's going to happen? Just kind of indicate. One of them going to go that way, one of them going to go this way. That's pretty obvious. Why? Because they're exerting equal and opposite forces on each other. So this one exerts a force in this direction. On this one exerts a force in that direction. On this one. Okay. So as you see, if you read your textbook, I hope you're doing that. F1 on 2. If this is 1 and this is 2, they would say F1 on 2. This is force exerted on this one by this one, right? And F2 on 1 is force here, and then equal and opposite. So 1 or 2. Which one's going to have the greater acceleration? 1 or 2 or equal? Forces are equal in magnitude. I would say the greater acceleration, one's going to be positive, one's going to be negative. Greater magnitude of acceleration. So which one has the greater magnitude of acceleration? Forces having same magnitude, the one with the lesser mass will have a greater acceleration. And we can confirm that. Okay. It didn't go very fast at all. Now, of course, my release might have been. But now what if I move this toward this? And what's going to happen? This thing's going to hit. The spring is going to compress, and it's going to be as if I was holding them together again. Okay. And then they release. Okay. Now, in this case, this one kept moving. Whereas if I release them, they kept moving in this direction. If I release them from rest, they go in opposite directions. Well, that's just because of the reference frame. We're naturally looking at it from the reference frame of the room. If you look at it from the reference frame of the center of mass, what's happening to the center of mass? if this thing's moving toward this one, center of mass is moving this way, right? If you're moving along with the center of mass, let's say, I'll have to try it later to see if I really could have it. It went in for myself on camera. If we're driving along here at the speed of the center of mass, then just like if you're passing another vehicle on the interstate or another vehicle is passing you, you don't see him moving at 80 miles an hour. Okay? Naturally, if he's moving 80 miles an hour, you're passing him pretty fast, right? Hopefully not, especially the cops around. Ain't really safe. What you see is you see him passing you at 10 miles an hour, or you're passing him at 10 miles an hour. And if you're driving along with the center of mass, what you see is the collision from this way. Okay? That's what you're going to see. You don't have to think about that a little bit. But that's not what it is. Now, the faster the center of mass is moving here, the more you're going to tend to see a backward motion of conservation momentum just chokes me up all the heck. You're going to tend to see this thing having more backward motion after the collision. You kind of want to think through how that works. I don't want to say too much about it without drawing a picture. Just think about it. First of all, what's happening to the center of mass? It's moving to the right, but not as fast as this thing, because this thing's still stationary, right? In any case, if you're doing the right speed, the collision is going to look fly apart. Okay, we're going to come to rest for a second to fly apart. Now, okay, the more mass you have here, more mass you have on this part. This part is stationary. The more the velocity here will exceed the velocity. So right now, let's say this has 3 times the mass of this. Then the collision point, this will move twice as far as this one. Now again, it's coming to rest because of the slope. We could measure the slope and figure out the component of the gravitational force in the direction down the incline. Also, there's a little bit of friction. These are engineers, so there's very little friction. But in what we're looking at here, we actually have a non-ideal collision, a collision where you have external forces. Remember your system here, if we define the system as these 2 parts, the system is exerting internal force. The force exerted here between the 2 parts is an internal force because it's one particle of the system exerting a force on the other and vice versa. 2 particles exerting equal and opposite forces of each other. External force is whatever the component of gravitational force is, apparently in this direction. And that could be measured if we know the mass. Start this thing moving, see how far it moves in 5 seconds, calculate the acceleration. Maybe move 10 centimeters in 5 seconds. That means the average velocity would be 2 centimeters per second. Okay? Which means initial 0.04, and you get about 0.8 centimeters per second squared, which is about 1,000th of the acceleration of gravity. And that's something to be able to calculate within the based on what we've done and how we think we've done that. Okay. So there's a situation. Might also be interested to see what happens here. And let's see. Pretty good. Obviously, external forces are at work here because immediately after a collision, this thing's going to be moving much faster than this is because they're exerting again forces equal and opposite forces of equal magnitude. This having about maybe 1/10 to 1/20 the mass of this, right? I don't know why. So it's almost come to rest. Anyhow, if you did a stop motion on this for the first 100th of a second after the collision, this would be moving much faster than this. But then you've got some acceleration there, so that's moving fast. That's whatever. Okay. So think about that. Think about what's going on. Think about how you would analyze it in terms of what you've already seen. If you're more than halfway through captain momentum. Where's the center of mass? What's the motion of the center of mass? These are all relevant things for understanding what's going on here. And especially the idea of the center of mass frame of reference, which we're going to talk about. Okay. I'm tempted to use a pool ball with this thing, but I don't think it's going to work out. So we're not going to do that. Okay, so after the collision, these two guys are stuck together. So what you have is total mass M1 plus M2 moving at velocity u. So let's say that u is your velocity after collision, common velocity. Without going through the details of the impulse momentum theory, wait a minute. I'm recording this and I'm not even still aimed over here. Hang on. Okay. There's a trick I can do to make this thing adjustment. I'm trying to avoid the watermark at the bottom of the screen. Okay, it's still recording. I didn't need to should pause about that. Again, what I've been saying is you got two masses, M1 and M2, moving at velocities V1 and V2. And maybe the velocity of this one's to the right, the velocity of this one's to the left. Maybe both velocities are to the right, but this one's going faster than this one. Now, you know, from driving on the interstate, say that if you're going faster than the car in front of you and stay in the same lane and don't slow down, if he doesn't speed up, you're going to hit him. There's going to be a collision, just like there would be if it was head on. It's going to be better if it was head on. And of course, you're going fast, maybe you drive both of you off the road, and that could be bad. But anyhow, you know, it can happen. You could even have a collision where one object passes through the other. For example, if I throw you a basketball and you shoot it with a .38 caliber gun, there's going to be a collision, but the basketball might well just keep going forward. So the bullet will be going through that basketball and keep coming at you, and keep coming at whatever you aim at. Okay, so anyhow. So all kinds of collisions, all kinds of things can happen. Two galaxies can collide. They can collide in such a way that almost no stars collide with each other, because stars are, you know, got lots of space between them. Okay, but their gravitational force will still interact, and they'll pretty much pass right through each other. Now, there are going to be internal changes in the dynamics of the particles in both the stars and in both galaxies. They have a collision where one passes through the other. And if they don't lose too many stars to each other, they maintain pretty much their mass, so their total momentum is going to remain constant. And even if they exchange masses, their total momentum is going to be constant. Okay? Even if you got a lot of collisions of stars, total momentum is constant. The idea is, though, that one object can pass through another one while interacting with it. And we could even do that with magnets. You know, have a frame with a couple of magnets here, and then shoot another magnet through that frame. It never touches the other frame, it passes through it, but it's going to affect the momentum of both, because everything is exerting equal and opposite forces on one another. Everything in this one is exerting equal and opposite forces, everything in that one. Okay, so collisions can be pretty general, but yes, this is more tangible, so we're going to analyze this one. So velocities before collision, V1 and V2, masses are M1 and M2. After the collision, if it's an inelastic collision, for example, a collision between two cars is pretty much inelastic. After collision, the cars are not necessarily stuck together, but there's a tendency for, you know, bumpers to interlock and stuff like that. Okay, usually they'll bounce off each other to an extent, but it depends on the collision. If they are stuck together, total mass is going to be the sum of the two masses, and you got some velocity u after collision. And if you know these two velocities, you calculate this one. Or if you know this one and this one, you can calculate this one. And the equations are easy enough to solve. Okay, so what's the equation that governs this? One way of writing the equation is that the momentum before equals the momentum after. Another way is momentum before plus momentum after equals 0. Sum of all the momentum. Okay. Before added to all the momentum after is going to be 0. Okay, well, momentum before equals momentum after. So what's the momentum before? Well, it's M1. Okay. Now, I don't have arrows over these because I'm going to assume this is in one dimension for the moment. So that these are just going to be signed numbers, positive or negative. This is positive direction where I've got the arrows, and this will be positive. Because we have B2 would be negative, B1 would be positive, and U collision isn't inelastic, then the right-hand side would be M1U1 plus M2U2. You'd have a U1 and a U2 after collision. That would probably illustrate that, but I think you've already done some problems of that nature. Okay, so here we have it. So if we know this, and this, and this, which we do, if we know these four quantities, masses before and the velocities before, then we calculate the velocity after on the assumption that the collision is inelastic. Okay? Or if we're given M1, M2, V1, and U, the only thing we don't know is V2. We can solve. So etc. Okay. Now, if we know that the collision is elastic, okay, well, another thing about the inelastic collision for and you've done this in the homework, kinetic energy is not conserved. Okay? You can easily prove it. Kinetic energy is not conserved. So what happens to all the energy that's no longer in the form of kinetic energy? Well, that's in the form of thermal energy typically. You know, if it's two cars, you're bending steel. Okay, you bend steel, it gets hot. And it doesn't take a whole lot of kinetic energy. I mean, it takes a whole lot of kinetic energy to heat up steel. Even more to heat up water per kilogram. So it takes, again, quite a bit of energy to heat most substances up. So you don't have to have a whole lot of temperature change to account for all that kinetic energy loss. Okay, we're not going to quantify that. That's a second semester topic. But that's getting into thermodynamics. Okay, now elastic collision. Kinetic energy is conserved. Total kinetic energy after equals total kinetic energy before. So in this case, maybe typically have M1 with velocity in maybe this direction. M2 with velocity U2. Okay, well, I'm going to have to say a little more about elastic collision. Really pretty important, especially when you're dealing with cases where they actually occur, which is like in the subatomic realm. Relative velocity after the collision equals the relative velocity before the collision. Now you can prove that. You can write out m1v1 plus m2v2 equals m1u1 plus m2u2, and m1v1 squared plus m2v2 squared equals m1u1 squared plus m2u2 squared. In other words, the expressions for the kinetic energy before and after. Okay, after the equal. That's two simultaneous equations. You can eliminate some variables, and you conclude this. Now, the way that's going to look, what's the relative velocity? If, I'll just gesture with my hand, if this cart is moving toward this one, okay, and this one's moving at 2 meters per second, and this one's moving at 3 meters per second, what's the relative velocity? If you're sitting in this car, how fast does it look like this one is coming toward you? Give me some fingers. Okay. No, not that. Okay. We're playing football. Not to intimidate you, but if I'm running toward you at 3 meters per second, your natural reaction would be to run away as fast as you can, obviously. Okay. Mine's going to be not to hit you because I'm not held together as well as I used to be. Might be fun. Okay. 3 meters per second is not that fast. I don't think I want to do that. Okay, anyhow. I'm running toward you at 3 meters per second. You're running toward me at 2 meters per second. How quickly am I approaching you? How many meters per second? Yeah. Okay. And you're approaching me at 5 meters per second. Okay. Now, one of us is moving in the positive direction, one's moving in the negative direction, presumably, right? So maybe our relative velocity, as I perceive it, you're moving toward me at 5 meters per second, but I think this is the positive direction. So I think your velocity is negative 5 meters per second, right? Okay. If you agree that everybody should look at things from my perspective, and you think our relative velocity is plus 5 meters per second, okay? But you usually don't think you're moving in the negative direction, so you're not thinking like I am. So one of us is screwed up. Not really, but okay, you agree on a common x-axis. And then the relative velocity as you see it is equal and opposite to the relative velocity as I see it. Okay. Well, okay, in this case, if this is a positive direction, I'm moving toward you, and you're moving toward me. What arithmetic do you do to get the relative velocity? Okay. You take my velocity, 2 meters per second, and subtract your velocity. Well, first, my velocity is 2 meters per second. Yours is negative 3 meters per second. Which is a fraction. What do you get? You get plus 5. Okay? That's not right. Because if this is a positive direction, your relative velocity with me is negative 5 meters per second. Okay? Now, if you follow that reasoning, you want to think about it, and I'm not going to give you time to let that sink in, so you kind of want to make yourself think about it, or when you read about it, remember what we said here. relative velocity will be v2 minus v1. Okay. So we'll take that as the relative velocity. Now, if after collision, u1 is negative 2 meters per second, u2 is 3 meters per second. I could say from V1 perspective, we'll say from M1 perspective. I didn't finish this calculation. Let's get the numbers to make sure we understand. It's negative 2 meters per second minus 3 meters per second, right? Okay. Relative velocity here will be plus 5 meters per second. Okay. So that's consistent, depending what the masses are, maybe it's totally consistent. But at least this much is consistent with what I said. The relative velocity after is equal to the, I said it's equal to the relative velocity before. It's the negative of the relative velocity before, equal and opposite. Okay. Said it wrong. And the magnitudes are equal and opposite. Okay, well, this collision makes sense. Okay. If you're a little more massive than I am, or at time a little more massive than you are, then you're going to bounce off in the opposite direction with greater velocity or with the lesser speed. Okay. Think about that. But that should match your intuition if you've done the problems, thought about them, and developed the intuition to go for that. And of course, it's still developing because it's just, we just started this chapter a couple of days ago. So now, for elastic, collision. V2 minus V1 is equal and opposite to U2 minus V1. Relative velocity before, from, in this case, from the perspective of V1, is equal and opposite to the relative velocity after with respect to the mass. Okay. Relative velocity with respect to M1, relative velocity with respect to M1. Okay. And of course, I could write this in the perspective of mass 2. For mass 2, the relative velocity would be V1 minus V2. And here it would be U1 minus U2. If I change the signs on both sides, that's exactly what I get, that those two would be equal. So it's the same. It doesn't matter from which perspective you observe it. The relative velocity, as long as it's observed from the same mass, is going to be the same. So if you write this backwards, it's equivalent. So you don't have to remember which way, which one goes first, which one's minus and which one's plus. You pick that out of a hat. Just make sure they go in the same direction both ways. If it's V1 minus V2 here, that'll going to be U1 minus U2 here. And one of the sides has to have a negative in front of it all. Okay? Again, ideally, you want to be able to just reason it out in terms of this simple as that. Okay? You probably don't want to think of running toward me because you don't want to end up having to call the rescue squad and everything. Okay? But just think of two football players running toward each other. Okay? Okay. Well, now, once you've identified this, it's pretty easy. So let's see if this really is a realistic collision. And it turns out that it is if the masses are equal. If the masses are unequal. Okay, so okay. Don't think anybody in here is 100 kilograms. 100 a little more than 70. 100 kilograms would be about 220 pounds, 224 pounds. Okay. Some of you are probably in the neighborhood of 200, but I don't know. I don't think anybody's 220 unless people are denser than they look. I'm pretty dense. But metal doesn't count. Okay, so V1 okay, we've got 3 meters per second and negative 2 meters per second. And the collision's elastic, so I'll write it out with the numbers. Here's conservation of momentum. Mass times velocity plus mass times velocity before equals mass times the unknown velocity after mass times the unknown velocity before. Okay? And I don't think that we're going to get these numbers. I don't think we're going to get negative 2 meters per second and 3 meters per second, although it might be fairly close. Then and I'm going to put my U's on this side, and I'm not going to look at these equations. Okay, I don't care if I've got the right equation or not, because I've got them subtracted in order with a negative sign in front of one side, right? So this is totally equivalent to this or this. There are at least 4 different ways to write this. Okay, and even more if we start distributing the signs. Okay. So what have I got? I've got 2 equations. With 2 unknowns, right? Now, V2 and V1 aren't unknown, right? Oh, hang on. Thing I like about using Zoom, the things I don't like about it, but one thing I do like. Okay, good. Now, let's see. Not seeing the whole picture. Not seeing the top of the board. If I go to the top of the board, there's going to be a watermark that wipes out everything over here. So I've got to play with this for a second. Let's see if I zoom in a little bit and lower this thing. And then zoom back out enough. It's kind of lower than I want it, but it's high enough that I think the watermark will be a problem. Trying to stay aware of the watermark because I have that on the video. Okay. We had a correction. I wrote U1 equals -2 meters per second instead of V2 equals -2 meters per second. Okay. So what I said earlier about U1 and U2 being the unknowns, it's what I intended, but it's not what I wrote. So I corrected that. That's not V2. So thank you for pointing that out. Now, we have this, and we conclude then that U2 minus U1 is negative of -2 meters per second minus 3 meters per second, which equals 5 meters. Well, I don't know if I got it. Okay. So we want to be aware of everything I've got over here, but we can't see it all anyway. Move this. Move this over a bit. Continue the problem. Okay. Okay, so now we have this equation. And U1 minus U2 equals 5 meters per second. That's two simultaneous equations in U1 and U2. Now, in this equation, every term has a kilogram on it, right? So I'm sure that my units are right because every term here has a kilogram and every velocity has a meter per second. Except over here, I don't have any meter per second. Well, I can divide through by kilogram, not have to write that. So over here, I get this equation. I get 300 meters per second plus, well, minus 140 meters per second equals 100 U1 plus 70 U2. So my units get a lot simpler. And we can see now that if I knew U1 and U2, they'd be in meters per second, that would match. So whatever my solution is for U1 and U2, they both have to be in meters per second because these are in meters per second. And of course, this becomes just 160 meters per second equals 100 U1 plus 70 U2. Easy enough. Okay, second equation, U2 minus U1 equals 5 meters per second. How can I solve two simultaneous equations? I can use elimination, I can use substitution. I could graph them. See where the lines intersect. Okay. If you don't know how to do all that, you really need to. Okay. Especially if linear algebra is still in your future. You just have to start the course knowing how to do that. That's high school. High school math. Simultaneous equations. 2 or 3 equations. Okay. It gets covered in a linear algebra course, but don't already know how to do it, you're going to have to solve it. At some point, make yourself a note to get that out of the way. If you had linear algebra, you know what to do. Actually, maybe not, because we're not going to do this with matrices. Okay, so we solve. Second equation for either U1 or U2, then we substitute that in the first equation, and now we've only got one variable in the first equation, and it's real easy to solve. Okay, so I'm going to get U2 equals U1 plus 5 meters per second. Substitute in the first equation, and you get 160 meters per second equals 100 U1 plus 70 U2. The U2 is U1 plus 5 meters per second. And you just turn the crank. You're going to get 170 U1 on this side. You're going to have 70 times 5, 350 meters per second on this side, which will subtract from both sides, giving you out of 70 U1 equals negative 190 meters per second. And the rest of the solution is straightforward. Got that? So U2 has to be U1 plus 5 meters per second. And 17 times 5, everybody knows, is 85. Subtract 19, you get 66. Okay, so that's a little over negative 1 meter per second. And this is 4.5, around 4, a little less than 4 meters per second. So a little more than 1 meter per second back this way, a little less than 3 meters per second, 4 meters per second that way. Now, to check this, what else is kinetic energy conserved? I'm not going to do that because you've had a number of problems, I think, already where you're asked to check the kinetic energy. Okay, but just to write it out and make sure. I'm not going to do the calculations because I probably already messed them up, but is the kinetic energy before equal to the kinetic energy after. So it's 1/2 times 100 kilograms. Make sure I've got my times Okay, there's my kinetic energy the first, kinetic energy the second. And then we got the mv squared after equation. Now, this is fairly easy. Of course, we can then divide out all the kilograms in the meters per second squared, right? And we just get pure numbers. And we get rid of the 1/2. Don't have to worry about the 1/2. 153 by 2 or divide through by 1/2. So we get 100 times 9 plus 70 times 4 equals 100 times, well, that's 361 over 279 plus 70 times 66 squared. Why did I do this? 66 squared. Okay, well, it's 3,600 and 720 is 4320 and 32 is 4356. It's 289, not 279. Okay. Well, you can check the numbers. But this is going to be fairly close to 16 times 70. Okay. And that's 1120. Now it's going to be maybe 130. About 1,300. And over here we get 900, 400, or 280. Which is 1280, which is close to 1,300. So even though the fractions don't look all that encouraging, I kind of think maybe I did it right. Okay. Now the point is not my arithmetic. That's just straightforward, and you know I'm going to mess it up. So do it yourself. But process. We have two simultaneous equations. For U1 and U2, this equation, and we'll use this one. So we write them out with the numbers and stuff, and we solve them. Or we could just solve them symbolically, and we still get a solution. Then we check if kinetic energy is conserved, chances are we did it right. Okay. To be really sure, you can also check momentum conservation. Total momentum before equals total momentum after. I'm not sure. Screen I'm saying is backwards. So could be, you've got a big old watermark down here. I was doing this stuff. Let me just do this way over. So if you look at the video, you can see what I did. I think the watermark will be below the screen, or below the board, but can't be sure. Still recording, didn't need to record those comments, but that won't hurt anything.